Hello again, and welcome back to my computer vision series. Today I'm going to talk more about deformable DETR. So in my last video, I've talked through the algorithm itself and the explanation of how it all works. Today I will talk about the code. So how to download the code, how to run it, how to train your own model to implement the benchmark, how to debug it, and hopefully that either helps you just use that model on your own, or maybe understand little details more, like all the intrinsic stuff that's happening here, to see it with your own eyes, to see it happen, to print out intermediate variables, and so on. So this is my plan for today. So first, I'll show how to set everything up and start training. Then I'll briefly show my debugging setup. What I do to make it easy to read the code and run it. Then we'll dig into the actual model architecture and encode for that. So starting with the multi-scale output from the backbone and how all of that is fed into the transformer. Then we'll look at the code for Deformable Self-Attention and Deformable Cross-Attention. So the code itself looks really similar to just the basic DETR. And I have a video about the basic DETR as well, algorithm as well as reading the code. So today I'm not going to repeat a lot of stuff. So I'm going to use that video as a foundation. So again, if you are unsure about some things that are happening right now, check this other video about reading the code for DETR. Okay, so first, where to get the actual source code? I can just Google deformable DETR source code, and the very first link leads to Fundamental Vision, and this is the original repository with deformable DETR implementation. So we'll need to check this out to clone it and to do some installation steps. So here they have instructions on how to do it. Unfortunately, the actual deformable layer itself only works on CUDA. So you will not be able to run it on Mac, you will not be able to run it on CPU. The only way to run this is to have a machine with the actual GPU and CUDA installed. And because of that, because of this user-defined layer, it also takes a bit extra in terms of installation. So they suggest using Conda, Anaconda or Miniconda. And I've tried different steps to do this, and Conda was really the only one that worked. So first they ask to install some initial libraries using Conda. So Conda, Anaconda, or Miniconda is one of the standard ways to set up virtual environments for Python and install different libraries. So I've tried exactly what they suggest here, and it doesn't work because my GPU is too modern for this, I guess. So this repository is 4 years old. So instead, I have my own instruction that I wrote that works for me, and it's a bit more up to date. So we're going to go with that one. So I'm going to create environment with Python 3.10. And then install slightly more modern versions of main libraries that we need. So PyTorch, TorchVision, CUDA Toolkit, and so on. So first I'm activating. And then installing. Then I need to install the actual requirements in this repository. And the final one is to compile this custom CUDA layer. So I'm going to model/ops within the repository that I just downloaded. And then I run make.sh. So in my case, it was already compiled, so it worked pretty quick. In your case, it's probably going to be a bit longer. But if you don't see any errors, then probably it worked. And let's just run this test.py to see, to make sure that it actually is installed correctly. And we can see that at least initial tests are okay, so it seems that it's fine. And the final test failed because my GPU ran out of memory. Now, hopefully that doesn't happen with the actual model, but let's see. Now, we need to get the data. So again, I just go to Coco dataset in Google, go to Coco dataset website, datasets, download, and then from here I need 2017 version of train images, test images, and then these train val annotations. So just download that, unpack it, and put into a folder. So in my case, that's datasets Coco regional. And you can see here that it has unpacked annotations, train, and validation folders. And this is how I run the actual script. So I run main.py, provide the output dir, the directory, the Coco path, and it should work. Sorry, I need to be in the root of the repository. Now this should work, but it doesn't. So it complains about something like new empty tensor op. So before we deal with that, let's configure Visual Studio Code. So I'm running this on a remote machine with actual GPU. I'm recording this on Mac, and then this remote machine has Ubuntu and GPU installed. So I'm opening a new window. I can just SSH to the same machine. Open the root of the repository. And there it is. So this is now the code from a remote machine opened in my Visual Studio Code. Let's look at the error once again. So it complains about this MISC file. Let's see what it is. So the problem here is that they actually parse the Torch Vision version incorrectly. So this one says, is it less than 0.5 or not? I believe mine is something like 116, which is not less than 0.5 if you compare it like that. So it's basically incorrect comparison. So they compare it to 0.5, 0.7. In my case, that's 0.16. So I'll just erase all of that, and then this should work. Yep, at least it looks like it starts to run now. Yep, so we can see that the epoch has started. We have our ATA for the first epoch, and a bunch of parameters with errors and stuff like that. So I'm going to interrupt that. At least it runs now. So that's how we set it up. So once again, we had to download the repository, install all the requirements, compile the actual CUDA layer. That is only possible on CUDA with on actual GPU. So it can't work on CPU, it can't work on MPS device. Then we downloaded the dataset. Then we had to fix one problem in the original repository with incorrect version parsing, and now it works. Now that it runs, I want to show you my debugging setup. So the tools I use that help me debug and read the code efficiently. So I've showed you before that I have my Visual Studio Code, and it allows me to do code navigation. So this is the main function, for example. I can just right-click on any function I see, like build dataset, and most likely I will be able to go to definition, which allows me to quickly navigate between the code. Next, I want to have my debugger so that I can launch the same script, break at certain lines, and just see what happens, step through that line by line. So to do that, I go to the Run and Debug tab in Visual Studio Code and say to create a configuration. So I'm creating a configuration for Python file, and it will have some parameters that I need to specify. So all of that can just be left at default. Then just my code, I'm going to set it to false, which means that I want to be able to step into PyTorch functions, third library functions that are not defined in this repository, but are defined elsewhere, and I will still be able to debug them. And finally, to launch the script, I also need to provide some arguments because it needs to know where the dataset is and so on. And I'm just going to copy that from the command line that I've just did, and just put it here. So now this should work. Let me try to run it one more time. I'll break at one specified location in the beginning of the main function, which will be really helpful to print out the actual values of the arguments, because a lot of them have some default values. So let's see if it works. So it worked. You can see from this button here, for example, that it's currently in the middle of this line. I can go to my debug console and print out the value for the arguments. And then I can step to the next line, or maybe continue until the next breakpoint, and so on. So I'm going to interrupt that. So this is how I get the initial values and maybe debug the code. I also have the Jupyter notebook. So I've just created a new one in the repository itself, and then basically just copy pasted a lot of code from just from the main function here. And some of it is from my previous video about DETR that are just helper functions to plot stuff and so on. So thanks to the fact that I've put this Jupyter notebook right at the root of the repository, I can now import custom modules defined here. So I can just copy the imports from here. So some of them use third-party libraries like argparse, JSON, and so on. And then some of them use functions defined in some other files that build the model here. Thanks to the fact that I put my Jupyter notebook in the same location, I can just copy-paste all of that, and it will just work. So next I have a bunch of helper functions with labels, with plotting. So I do unnormalization during plotting to make sure that I can provide the actual output of the dataset that does pixel normalization and convert it to the format expected by the plotting function. Then I have this args helper class. So in main.py, most of the parameters being passed around are defined as the command line arguments. It's not really easy to provide command line arguments for Jupyter Notebook. And you can see in the code that most of the functions use this arg variable. But we can recreate the same variable by just creating a custom class, inheriting from this argparse.namespace. And then I just basically copy all this stuff here and define that as just common Python fields. And then I define my variable like this. So now I have this args that looks somewhat like command line arguments. And because of that, I can just keep passing that around and it should work. So now I can access it the same way it is accessed in the main.py, which allows me to just keep copy-pasting the code from main.py here and just execute it line by line, which is really convenient. So we have our data set that allows us to load the images. Here's how we can print out the content. So I'm printing out the shapes of the first two images and the labels. So again, the data set, you can access it kind of like Python list. So you give it an index and it gives you back an example. An example in this case consists of an image and labels. So we can see that all images have slightly different shapes, and we'll need to be dealing with that a bit later. And then labels is just a dictionary with actual bounding box coordinates, actual class labels, and some stuff that is not used for object detection but might be used for other tasks. And here's how we can plot the results. So this image can be familiar by now, so it's the first one in the COCO dataset. We can keep running this cell to test what image transformations are used. We can see that sometimes the image flips left to right. Sometimes it gets cropped out. So the dataset uses what's called random resize crop. When you first choose a random portion of the image and crop it out, and then you rescale it a little bit to change the aspect ratio. And that's about all transforms used here. And then we have the data set, or the data loader. So the data set is just the thing that deals with the actual images, loaded them from disk. And then data loader loads the data from the data set. So it iterates over the data set with the indices. It deals with shuffling. It deals with buffering so that you read up some of the data in advance to make sure that you always have enough data loaded and transformed and ready to be used, so that when your GPU is done with its batch, it can just start with the next batch at once, and it doesn't have to wait for transforms to happen or for image to be loaded from disk. Then data loader also has to unite different images into batch. And in here, since the images all have different shapes, we also have this collate function that deals with that. And basically it pads the images with gray areas around the edges to pad them all to same dimensions, the maximum dimensions within the batch. But then it also returns the mask, so the Boolean tensor with true and false, that actually lets us know which parts of the image belong to padding and which parts of the image are real. So we can get the first example, the first batch out of the dataset like this, just with a for loop and then just break after the first iteration. So now X is a nested tensor. Nested tensor is a class defined somewhere in this repo as well. So we can access the actual tensors, so the images of the batch with x.tensors, and we can access mask with x.mask. And here is how it looks like. So this is the first image in the batch, and we can see some gray area on the bottom, and this comes from padding. Now let's also look at the second element. So now it has padding on the right. So this is how it works. And finally, we just build the model. Again, all of this code I just copy pasted from main.py function. I get the model. I have my batch now, so I can now feed the batch into the model and get the output. So this should work. And it worked. So most of the remaining video will actually be about what is happening in this precise line. So we'll actually use debugger to step through the model inference and read it line by line and understand what's happening. Here we can at least understand the output. So we have a dictionary of logits, class probabilities, and then bounding box coordinates. So we have two images in the batch. For each image, the model outputs 300 predictions corresponding to 300 experts, 300 potential objects that can be in the picture. So the old DETR used just 100. Here we use 300. Then we have 91 classes. So 90 COCO dataset classes and then one extra class for no object. So most of the experts, most of these 300 should actually output no object class. And then we have another prediction for 4 bounding box coordinates. Okay, so now that we can launch our model, can debug it in Jupyter Notebook, let's start reading the actual model code. And we'll start with the backbone output and how the entire multi-scale stuff is working. So here is the picture from the paper of the overall model architecture. So this is the part with the backbone. So we have our model like ResNet 50 that takes in the initial image, passes it through a series of convolutions with some stride that downsamples it to smaller resolution, but then more feature channels, more feature maps, and the output of that is like more processed, more refined representation of the image. But we also take these intermediate outputs as well. So we want more feature maps that are maybe less processed, but with higher resolution. So let's try to read that in code. So I'm back to my Jupyter notebook where I have a line of code that does the inference. I want to come back to this build model function and set some more breakpoints. So we can see here that the main model being returned is this deformable DETR. So just go to that one. So it inherits from nn.module, which basically means that it's a classical neural network. And it should have at least two methods. So the init method that's used for construction, and then somewhere here, the forward method that is being called whenever you call the model. So I'm just putting the breakpoint right here in the very beginning. And I'm back to my Jupyter notebook, and I just press debug cell. And here we are. So I've stopped at the very beginning of this forward method. So first, let's actually print out what we get in as samples. So it's a nested tensor, so it will have tensors and mask. So let's print the shape of tensors. That's 2 by 3 by 1063 by 813. So 2 stands for batch dimension. We have 2 images in a batch, 3 color dimensions, and then this 1000 by 800 quite high resolution image. So I pass that through the backbone, and let me just print out the shapes of the result. So now this features output is a list, and the length of that is 3. And let me just print all the intermediate shapes. So we have 3 outputs of the backbone that correspond to these 3 different levels. And you can see that the first one has the highest resolution, 100 by 100, then something like 60 by 50, and then the final one is the smallest one, lowest resolution, 34 by 26, but then the most channels, 2048. Let's go forward and see what happens here. So I'm just continuing until the next if condition. So now we have this self.num feature levels variable. Let's print that out. So it says 4. So I got 3 levels as a backbone output, but my model says that I want 4 levels. So what's happening here is that I'm going to create an extra 4th level by basically applying my own set of convolutions on top of the last scale from the backbone, the one with this lowest resolution. So yeah, this is what happens. So we can see where it is defined. It's this input proj list that's being combined into just a sequential layer, basically. And it's a combination of conv2d and group norm. So conv2d is just a normal convolution, similar to what there are in Backbone, in ResNet. We also have this group norm. So in various different models, we've seen batch norm, which is the most standard one, that does the normalization by taking these statistics, the mean and standard deviation, from the batch, but not from different channels. So we only focus on one coordinate, on one channel within current layer, and then we compute the statistics over the sample of the batch and use that to normalize the result. Now, in our case, batch size is just 2, so we can't really use that because it's too small for proper statistics, and it's 2 because we want to train on like multiple GPUs, and every GPU will have its own batch and so on. So another normalization we've seen is layer norm, which is used in transformers, for example, that doesn't look at different images in the batch, but instead it looks at all the coordinates, all the channels in the current layer. That might work, but as practice shows, it's not ideal because different features, different feature maps might actually be different. So some of them might be like detectors of something in the original image. Some of them might be just used by the network to pass on some information that's important to it and not necessarily detect any specific objects. And so we want to give the network this ability to express just various kinds of features at the same time. And to do that, we use group norm. So we basically provide the network with, 2,000 channels, but then we divide them by eight groups, and normalize each group individually, which means that now we have these 8 groups of different features, and the model might learn to put different stuff in different groups. So that's what is used here. So I use my last level, the third level from the backbone, pass it through my input projector to get the fourth one, and then just append it here. So let me continue up until this transformer input here, and just print this length of this list, for example. So we now get 4 different levels, and the last level is even smaller than we've seen before. So the third one was 34 by 26, and now we have one of 17 by 13. So it is even smaller. And here's the actual input to the transformer. So apart from transformer, not much interesting is actually happening here. Just some conversions of the outputs and so on. So I'm going to remove the breakpoint and just go and just do another loop in the code. So executing the cell another one more time, and actually break at this transformer forward path. So here it is. So it is now deformable transformer. So this is the one called here, the transformer layer, and the forward pass for it. So now the input here should be still the same. So it's the 4 individual levels. Basically, I'm in here right now. I had my 3 levels from backbone output, and then I created another smaller one on top of that, just to be extra sure. And then somewhere here, I have the encoder, and there's a bunch of stuff happening. Let me just go to that. And there is a bunch of stuff happening that is quite complicated in these 20 lines of code. So we have the flattened source, spatial shapes, level start index, valid ratios, all of that. So let's discuss it, starting with maybe just level positional embedding. Before we flatten the input, we know which pixel comes from which level. But to pass it to encoder, we flatten it all out, so we lose all of that information. Similar to how we lose positional information, so where this pixel is located within the image. So we want to encode that explicitly by adding a special embedding for the position as well as for level. So we have an extra level encoding that helps us provide the network with the information about which level this particular pixel is coming from. So we get level positional embedding by just applying this self.level embed, which is defined here, and this is just a nn.parameter. So it's a trainable vector of parameters, basically. So the shape of that is 4 by 256. So 256 is our embedding dimension, and then we have 4 layers. So we have, so we basically have a vector for every one of them. Then we also have these valid ratios. So let's print out what that is. So it's 2 by 4 by 2. I can just print out all the valid ratios for the first image. And let me explain what that means. So when we do the deformable attention, we want to start somewhere, the head of this football player, for example, then find the reference points in the input corresponding to the same point in the picture. And that happens on different scales. So we'll have the head of my football player here, here, and here. And I then use that to compute offsets to look at the points I actually want to attend to. So offsets that are being predicted by the model are all relative. So they are all counting from a certain reference point. And the reference point in case of self-attention just comes from which point in the output am I computing at the moment. But the task is to basically project that specific point onto different resolution scales. And that is further complicated by the fact that I have padding. And because all the scales have different resolution, the actual pixel ratios of what is padding and what is not padding will be slightly different. And that's why we just explicitly save them and pass them through the model. So basically the valid ratio says, like, in this scale, what is the proportion of the height and width of the real image to the height and width of the actual image with padding that we are passing to the transformer, and same for different scales here. And that's what we see here. So for the first image, the height is always the same. So we're not padding anything vertically. And then the width ratio is slightly different. So it is close, but because of these mask interpolation that happens when I have to downscale my mask to a lower resolution, the actual ratios of pixels belonging to mask and pixels not belonging to mask will be slightly different. And that's what I pass in the valid ratios. Then the level start index is basically telling us what index belongs in the final flattened output belongs to which level. And then this flattened input is going to be a long sequence. So it's 2 by 18,088 by 256. So 256 is an embedding dimension, 2 is the patch dimension, and then we have 18K, this giant sequence that we pass on to our encoder. Okay, so we've seen how the image gets transformed from the backbone and gets passed into the encoder. So we've seen how the levels are handled, how all of that is flattened out, how the level positional embedding is added on top of the normal positional embedding. And now let's look at the actual deformable self-attention. So once again, we are going to look at this part of the model now. So input to every encoder layer is going to be this flattened out, multi-level, multi-scale feature map. And the output of each encoder layer will have the same shape. And we want to have this deformable attention where each point in the output decides on just a bunch of points where it wants to attend to. And the process of decision is basically predicting some offsets with respect to some reference point. So this is how the self-attention should look like. So we have our flattened image representation as queries, the same representation as values. We don't have key here. So in normal attention, we had queries, keys, and values. And then you would compute the dot product between all the queries and all the keys, so all the pairwise, all the possible pairs. In here, we just have the query, and we just use the query embedding to decide on the offsets, which basically means which points we're going to attend, and the attention weight itself. An important thing here is that offsets are all relative to some reference point. And we need to compute those reference points across different scales of the image with slightly varying padding because of the number of pixels that are present in each image. So this is like the main challenge with the self-attention now. Now let's read it in code. So before I continue my debugger execution, I want to set the breakpoint in the proper location. So encoder is defined as deformable transformer encoder. Let's go to that one. So here the forward pass is pretty easy, just 3 lines of code where we get the reference points and we just iterate over layers. And then most important stuff happens within the layers themselves. So the layer is this deformable transformer encoder layer. But it's still pretty short, right? So let's just break somewhere here and just see how all the variables look like. And then maybe we'll also drop down into this deformable attention function. Right, so now the source, the input tensor for this layer is the sequence that we've seen before. So 2 images, 256 embedding size, and then this huge 18K sequence. Then we have these reference points. So let's just discuss what that is. So the shape of that is 2 by 18K by 4 by 2. So these 2 dimensions we know. This one is for different levels. So we have 4 levels and we need a reference point for each of them. And then 2 are for X and Y coordinates. So this reference point sequence is the same length as the original sequence, which basically means that for every point in the output, I have a reference point that I need to attend to. So for example, for this football player head in the output, or the place of the output which represents this football player head, I need to find projections onto 4 different scales, including the fact that some of them will be padded, and the padding sizes are slightly different in every scale. So this is what reference points tell us. This is the fractional coordinate within the image that represents this within each scale, that represents where exactly this pixel should be located at every level. So now if we print, I know the first image, the first point, all of them are close to 0 because this is the first sequence element, so it's somewhere in the top left corner. Now let's see where the next level starts. So the next level starts at 13,566. So I can grab the sequence element number 13565, and that's going to be the last element in the first layer. And here all the reference points X and Y coordinates are close to 1. So now they are in the bottom right corner. So the actual self-attention function here is defined as this MS deformable attention layer that is defined right here in this repository. So it's not a PyTorch module, it's a custom module. Let's break on the forward pass of that and just see what we see here. So yeah, the input to that, we had our source, so our input tensor. So we pass it 2 times, one time with the positional embedding as a query, and then another time without the positional embedding as a value. We pass in the reference points, spatial shapes, and all that stuff. So now this is going to go down to this MS deform attention function dot apply, and then it has a bunch of stuff happening here. Coming back to the slide here, so to do deformable attention, we already have our query and value inputs. Now we have to project query into these offsets and attention weights. We have our reference points passed in as an input. And then we'll need to actually perform this attention. So sampling offsets, we get them by applying this self.sampling offsets layer. And this is just a linear layer. So let's print out the shapes of that. Or maybe just the shape of the output then. So it's 2 by 18,000K, that's our sequence length, and then a bunch of numbers. So let's find out what it is. So first of all, we have multi-headed attention. So whatever it is I was showing in the slide, that actually happens 8 times. So we perform the same operation 8 times for 8 different attention heads. That's the first 8 here. Then we have 4 different scales. So for every sequence element in the output, we attend to 4 different scales, 4 different levels in the input. And then for every scale, every level, we also have 4 attention points. So maybe this element is going to attend to this, 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 and this. Only 4, exactly 4, independent on sequence length. So basically, to get these sampling offsets, I just take the query embedding for this certain element, and then just project that using my dense layer, the trainable dense layer. And I do the same with the attention layer. So attention weights is also just an n.linear. But now the output of attention weights, the shape of that is slightly smaller. So here it was 4 by 4 by 2, and here is 16, which is just 4 by 4, because offsets contain x and y coordinate, and attention weights just have the weight itself. So then we have our reference points. So reference points, they are all equal for all the attention heads and all the points that we want to attend to. So I have just one reference point, and I want to count out 4 different offsets with respect to that point. And I get sampling locations by taking these reference points, broadcasting them in such a way that I get like a copy of a reference point for every attention head, every of the 8 attention heads, and every of the 4 different points I want to attend to. And then adding these sampling offsets, the predicted value that I just got by taking the query, embedding, and applying just one dense layer to that. And here I get my sampling locations. So if we continue on to here, now the sampling location should have the same size as the offsets. And let's see, for example, the locations for the first image, first element in the sequence, first attention head, maybe first scale, and then all of the points, right? And you can see that they all sort of attend to the same y coordinate, but then slightly different x coordinates. And again, this is randomly initialized network at the moment. It's not trained yet. And for now, it is learning to attend to like the following sequence of just a row of pixels, basically. Now, I'd also like to show the actual deformable attention function. It is written in CUDA, so we'll read that briefly in a moment. For now, since CUDA code is going to be more complex, it's going to be in C++, it's going to be in a GPU kernel. So before even diving into that, let's just remember one more time what we expected to do. By now, we have our offsets, we have our sampling locations, which are reference points plus the offset. So we actually know in which location to look at. So for this point here, for example, we already know that we should attend to this element, and then basically take these embeddings, take the attention weights that we also have, and then just compute the weighted average. However, sampling locations are fractional. which means that the actual sampling location, the real number that might have fractional part, might not land on precisely the pixel. It might land somewhere in between. And because of that, we use bilinear interpolation to look at 4 nearest pixels in the 2D representation of the image, and to compute the value in that location as just bilinear approximation, basically a weighted average across these 4 pixels. So here's how it might look like. So in linear interpolation, where you just have 2 points, you just draw a line and then find the point that you're interested in. Then in bilinear, you have 4 points in 2D grid, and then your black point is somewhere in the middle, and then again you decide on the value for that one based on how close it is to all the neighboring pixels. So to sum up, if we didn't have these fractional locations, we could have just take one value tensor, take our sampling locations, and just use sampling locations as an index to look up the values of the output, and then just multiply it by the attention weights and get our output. And it's probably quite easy in just PyTorch code. Take one tensor, index into it using another tensor, and then multiply by attention weights. With the bilinear interpolation, there's no really ready function for that in PyTorch. So the authors of this deformable DETR had to write that from scratch. But this is what this function is going to do. So it's going to take these fractional indices and perform this fractional lookup, where I want to take a look at like pixel number 100 or pixel number 100.31 and approximate its value using the neighbors. So this is the only thing that's going to be custom CUDA code here. So now I'm going to try to find the definition for that. So it calls this msda.msDeformAttention forward. Now here is where my go to definition button stops working. But I can see just search that it's defined in this msDeformableAttention.h file. So it's CPP file now. And it forwards it to msDeformAttention CUDA forward, which is again a CPP file. Now here's a bunch of stuff that will be happening here. So first, a couple of words about CUDA. So CUDA is GPU code. But to call GPU, we need to dig into C++ as well. So we can't call CUDA kernel directly from Python. So we have to call some CPP function, and this is the function itself. So it's written using these PyTorch CPP objects. And we basically bridged from Python code into this CPP code, thanks to this basically build thingy that created the bindings from Python to CPP. We did that without any copying. So this is the good thing about the CPP API of PyTorch. So we had our tensor objects in Python, which are basically shallow pointers to the actual data, the actual long list of data that is, in our case, located on a GPU. And then the CPP function receives the same sort of shallow objects that point to the data that is located somewhere, either on CPU or GPU. And this layer only works on GPU. So we know that these tensors are located on GPU. Then we have a bunch of just CPP code that decides what to do next. And so in our case, it will iterate over all the images in the batch size. It will call this extra function. So my initial input was just a long sequence of elements, like 18,000 of them. And I need GPU for parallel computing. And it's obvious how to do parallel computing here, because you have this long sequence. You can just divide that into parts and then feed that part into separate GPU kernels. And you can judge by the triple triangle parenthesis here that this one is the call to the actual GPU kernel. So now I still get all the data, but now it's CPP. So we get the actual pointer, the raw pointer to the data somewhere. And we pass that to this MS Deformable GPU kernel function. So this is the function that will do all the work that's actually executed on GPU. And this is the definition for it. So now it does this CUDA kernel loop. And this CUDA kernel loop function defined right here, it uses these magic variables block IDX, block dim, and so on. So coming back to where we started. So yeah, first, what does this code do? So we've been in Python. We had our sampling locations and the values, and we need to do this basically fractional bilinear indexing. So first we had some CPP code that bridges over from Python in order to make the CUDA kernel available so that we can launch the actual code on GPU. And this CPP code basically receives a bunch of parameters and a huge array of data. So the 6-dimensional tensor that we've seen before with batch size times sequence length times number of heads, number of levels, number of points, all of that is passed in just as a raw pointer without any information like where specific heads and levels and so on actually live. But we have all the data to calculate that. So we receive the number of queries, number of attention heads, and so on. And the main problem with this CPP CUDA code is that now you need to be really careful about all of that. So you will need to compute like the actual pointer locations where the data that you have is supposed to be. So then from CPP code, we deal with parallelizing. So we decide how exactly we split the work across different GPU kernels. And in our case, that's pretty straightforward because we have a huge sequence length and we can just divide and send some sequence elements to some kernels and then other sequence elements to other kernels. And then we launch the actual GPU kernel. So the syntax behind the actual GPU kernels is that you create like 100,000 of them, or maybe 1,000 of them. Each of them knows which ID it has, and each of them just receives all the input data. But then knowing that I am ID number 3, for example, it knows which portion of the data to look at. And so this CUDA kernel loop cycle that we see here, that's basically iterating over all the pieces of work that this particular kernel has to do. So a kernel means that the code that you see here will already be executed on the GPU. So then the next thing we need to do here is to get our sampling points, which are fractional from 0 to 1, basically, telling us which part of the image to look at, and then convert them to the actual pointer locations. So we first look up the actual spatial dimensions of the image to know how many pixels wide and height we have, and then do some math to find out, like, starting from the start of this array, where this particular element has to be located. And then we do this bilinear interpolation. So if I go to definition here, this is where we'll see the actual logic for getting a fractional location that should tell us the pixel number, and then getting the nearest 4 pixels. So the floor here is basically taking in the fractional number, like 10.73, and then getting the floor of that to get the 10, which gets you like the topmost or leftmost nearest pixel, and then the same one plus 1, that's getting the rightmost or the pixel to the bottom. So now we have these indices of nearest pixels. Then we do some data checks to make sure that we are not looking at the data that does not belong to us. And then the actual value calculation is pretty simple. So we have this bilinear interpolation, which is just taking the weighted average of all the nearest pixels. And somewhere here, we also multiply by the actual attention weight. So this is the part that works in CUDA, in CPP code. So now returning to my Python code. So I've called this as Deform-Attention function apply. So once again, the input to that is the values and the fractional indexes that I need, including all the sampling locations that I need to take and the attention weight. So then this CUDA code just does this bilinear interpolation for approximating these fractional pixel values. And then we just take the weighted sum and return that. And that's return of our encoder layer. Now let's also take a look at the decoder layer, so at the cross-attention. That's the final part of the model. So now we have these object queries coming from the bottom. And queries, you can think of them as experts that actually judge the image. So in decoder, you'd have cross-attention. That's when the experts look at the actual refined image representation and then decide how to deal with that, how to find out the actual bounding box classes. You would have self-attention, where experts or queries interact with each other and make sure they don't do the same prediction and maybe exchange information. And as usual, you'd have a bunch of residual connections, normalizations, and just dense layers. So one important detail here that we'll need to take a closer look at are the reference points. So we've talked about the reference points in self-attention, and that's when, for calculating the certain sequence element in the output, we know which piece of the image this element corresponds to. So for example, this element corresponds to the head of our football player. And we can take the exact same location in the image throughout different levels in the input. So we just take the output location as the reference point. But in this case, when we have object queries, they are not located in the image space. So we don't have these a priori reference points to speak of. So we need to decide what the reference points should be. So we also predict offsets, but we also need to get the reference points from somewhere. And we get that by just applying fully connected layer to the object queries. So we take object queries, we apply fully connected layer to get the reference points, and we add offsets to that to find out where we need to attend to. And this is how deformable cross-attention should look like. So now we have queries that come from these 300 length input of experts. We have values coming from the image, basically. So values will represent the actual sequence elements of the image. And then once again, we project every query embedding to offsets and attention weights. We also project every query element to some reference point, as I've described before. And then we use these offsets to decide which particular elements with respect to this reference point to attend to and what should be the attention weights. And then we take these attention weights, compute the weighted sum of the values to get our output. Okay, now let's try to see all of that in code. So I'm just going to relaunch my model inference cell, and then I'm going to stop at a few key locations. So far, our model is like an onion with layers. So the outer layer is called DETR, which has backbone and the transformer. And then transformer has encoder and decoder. And then decoder itself has 6 layers. So we're going to look at those layers consecutively because they all have relevant logic for our decoder. So right now I am in the outermost layer called DETR, which has backbone and transformer. So here I have my transformer call, and I pass in my query embeddings. So query embeddings, let's type what that is. That's basically a trainable tensor with weights, and the shape of that is 300 by 512. So we have 300 experts. To be honest, I expected this to be 256 dimensional embedding, but it's twice bigger. and we'll see why in a second. But basically, decoder input can be seen as query position embedding, which is just independent of the content of the picture, and then the target, which initially should be initialized as zeros, at least how it was in the DETR. And then after the first layer, it's basically the output of the first layer, and then the output of the second layer, and so on. So we always mix in something with the query positional embeddings. And in here, instead of taking zeros as targets for the first layer input, we also have it as a learnable parameter. So now this query embedding actually contains two parts. So one that is only passed in as the input for the first layer, and another one that is passed to every other layer as well. So now let's go down to the transformer. So this is the beginning of the transformer input. And here we have some code for reference points. Now for encoder, reference points were relatively easy because I have my pixel in the output that actually corresponds to a specific point in an image, and I just use that as a reference point. Now with queries, with experts, we don't have any reference points to speak about, so we have to generate them from scratch. And we can see it happening right here. So I still have my query embedding, which is an image independent twice the size vector that I randomly initialize and train. Then I split that basically into two vectors, so query embedding and target. And then target will be used as the sort of replacement of input for the first layer, and then the query embed is the actual positional embedding. Then I create my reference points by calling this self.referencePoints layer. So the type of that is just a linear module. So I get my positional query embeddings and that project that to get my reference points. So the shape of that is 256 by 2. So I project 256 embedding into just 2 coordinates for the reference point. And then the actual reference points will have the shape of 2 by 300 by 2. So we have 2 images in a batch, 300 experts, and for each of them I have 2 coordinates x and y for the reference point. And then I call decoder using that. So I have my memory, which is encoder output. Let's also print the shape of that. That's our huge sequence of 18K elements. We pass that to decoder. So let's read the decoder code now. So again, decoder is like a wrapper on top of decoder layers. We can see that it basically iterates over the layers themselves. Not much interesting happening here. There is this bounding box refinement, which is false by default. So it was a separate paper, I believe, not exactly deformable DETR. So let's just dive into deformable layer. And now here is where the actual cross-attention happens. So this is the forward path. So I have my target, which for the first layer should be just the randomly initialized and trainable vector. Then sometimes I will mix that in with the query embedding, which is again just the learnable randomly initialized vector. So first I'm performing self-attention. It is defined above over here, and it is just calling pytorch.nn.multi-head attention. So the self-attention in the decoder is just the normal full attention between all the query and key pairs. So we don't use deformable attention here. We just use the normal attention because we just have 300 queries, so we can afford to compute all the combinations. Then, as usual, for query and key, we use the variant with the positional encoding. And then for value, we just use the target without positional embedding. Then the pluses here represent residuals. Then we have dropout. normalization, which is just layer norm, then the cross-attention. So now cross-attention is exactly the same deformable attention that we've seen in encoder, but in encoder, query and value both came from the image. And now query comes from our experts, 300 of them, and the value comes from the image. And it has like 18K sequence length. And that's about it. So we perform the same calculation 6 times. Then we have a bunch of extra dense layers to project these 256 dimensional embedding into class probabilities and bounding box coordinates. Then we have our bipartite matching loss. I would not talk about it again today because I have another video about the actual DETR that explains it quite well. So that's pretty much it. So this is it for today. I hope you enjoyed this video. I hope my explanations were clear enough to help you, to maybe explain the concept of deformable DETR better, or to help you set up the code and learn to read it by yourself. I really think that it's a very important thing to do in machine learning, to read the code, to read the code of the actual benchmarks, not just the tutorial code you might see in Coursera or somewhere online, where they tend to skip a lot of ugly details that might not be as interesting, but they're actually required to make stuff work. In addition to that, I have my channel, and the goal of my channel was to, first of all, create a learning path for everyone, so that if you are not sure where to start, you can just come there and understand the entire map of computer vision, and in the future, I hope other areas in machine learning as well, just to understand where you are right now, what you know and what you don't know, and what path to follow. In addition, I'm trying to explain fundamentals of things. So it's quite easy to find tutorials online about stable diffusion, about grounding dyno, something like that. But then finding the explanation of what is dyno, how does it work, how it is different to DETR or ResNet or other models, that's much harder. So I'm trying to fill that gap. So this is what we have in my channel at the moment. So we've started with something really simple, just digit classification with PyTorch with low resolution. That's a tutorial that you can just sit down and follow through in half an hour. Then we threw in a lot of details on top of that, like convolutions, activations, parameter initialization, residuals, batch norm, cross entropy loss, all of that, which builds the foundation for deep learning, for deeper models, more effective models. And we culminated that with a project of reading the code and re-implementing the benchmark of a ResNet. That's the winner of 2015 ImageNet Challenge, beating human performance in image recognition. Then we moved on to object detection. That's when you might have several objects in the picture and you need to localize them by drawing bounding boxes. Right now I have video about YOLO, about DETR, and I'm slowly moving on towards current state of the art on the COCO dataset in object detection. So we've discussed DETR, we'll discuss deformable DETR, and read the code for that. And the very next video in the series will be about dynamic anchor boxes, also called DAP-DETR. That's just another step on the road towards state of the art. So there'll be a bunch of steps in the future, so we'll get to that. In addition, I also have a video about neural style transfer, which starts a new branch in generative AI. And in that branch, I'm hoping to tell a lot of stuff to build the foundation of like what are modern generative AI models doing. So that's variational autoencoders, diffusion, GANs, how to generate images unconditionally, so that you just have a model, you click a button, and you generate an image. And then we'll have a long way to build the conditional image generation. That's when you have text prompt, you feed it into the model, and the model generates something based on the text prompt. So we have a lot of ground to cover. So I hope to see you soon. Goodbye.